Welcome to the Chapter 3 lecture for plate tectonics. I'm just going to go ahead and jump right into the lecture today as this is one of the most important topics we're going to be discussing for this class. Many other hazards hinge on your understanding of plate tectonics, so please do take your time. Have your notes packet printed out and ready to go. Hopefully you've already read Chapter 3 so that we're on the same page. So, starting out at the top of your notes, we've got the same image here, and we're looking at these different features on the Earth's surface. So I want you to take a minute and look at this image you've probably seen many times before. Try and notice the highs, the lows. Is it a consistent elevation everywhere on the continents? Is it a consistent elevation everywhere in the ocean? Alright, so taking a look at those features, those high points and low points, we're going to figure out what those are. What are the main features on the Earth we're going to be talking about in this lecture and in this class. And then in your notes I'd like you to note whether it's located in the ocean, on the land, or on the border between ocean and land. So the first feature we're going to be looking at is an oceanic fracture zone. So your feature is the oceanic fracture zone. The location is in the ocean. So what this is pointing at is the roughly horizontal line going across the ocean. So this is where the oceanic plate is broken, is fractured. And so if you look below that, you can see there's several other roughly horizontal lines below that. And once you get used to looking at that, you can see them all over in other parts of the ocean floor. So our first feature is the oceanic fracture zone. Our next feature is the linear island chain. So this is located in the ocean because it's an island. And it is just what it says it is, a linear chain of islands. So all of the islands are lining up right in order. And again, this is a feature that can be found in various places on the Earth. So once you notice it, where we're pointing at right here on our map, you can notice it in other places where islands are making a roughly straight line. Our next feature is the deep ocean trenches. So this one we're looking at the western coast of South America, and this is going to be located on the border. So technically this is in the ocean, but it's right on the edge between the ocean and the continent. So the deep ocean trench is our next feature, followed by the mid-ocean ridge. So this is located in the ocean, and that is the jagged line. It almost looks like a zipper running up the center of the Atlantic Ocean here, in between South America and Africa, in between North America and Europe, all the way up to Iceland. This is the Mid-Atlantic Ridge, and you can find mid-ocean ridges elsewhere, but this is the best example. So again, mid-ocean ridges located in the ocean. Our next is oceanic plateau. This is just an area of higher elevation that's relatively consistent. So it's a higher flat area, still below sea level though, so still underwater. Oceanic plateaus located in the ocean. That covers most of our oceanic features. Now we can talk about continents. So continents, again, if you recall to last week's lecture, we talked about isostasy and the thickness of the crust. Continental crust is much thicker than oceanic crust, and so it sits up higher above sea level. The rocks are less dense. They're felsic, meaning they're composed mostly of these light-colored, less dense minerals. So again, continents are going to be at higher elevations than any of the oceanic features. So this is located on the land. Another feature located in the ocean would be submerged ridges and island arcs. A ridge is just basically a mountain range, and in this case it's a mountain range associated with islands. So if it's submerged, that just means it's underwater, and island arcs mean the islands, as opposed to the linear island chains which form nice relatively straight lines. An island arc is making a semicircle shape. It's an arc of islands. Next we have continental shelves, and this falls under the category of on the border between ocean and land. This is the shallow area adjacent to continents. So that's the light blue area. You can see up around northern Europe. We can see it very clearly around Australia, Indonesia, around the southeastern edge of South America, and so on. Anytime you see this light blue area, we're looking at the continental shelf. That's a shallow area that is part of the continent but is submerged. Next we have plateaus, and plateaus are just high elevations that are relatively consistent. So in this case we're looking at the Tibetan Plateau, where India meets with the rest of Asia, and this is in the Himalaya Mountains. So very much on land. Now that we've covered those different types of features and you know what we're looking for, I want to talk about earthquakes. Where do most earthquakes occur is the question in your notes. So taking a look at this image here, each yellow dot represents an earthquake. So just think to yourself, where do I see these earthquakes occurring? Is it a perfect grid where it's evenly distributed across the globe? No. Does it all occur on one continent? No. It's distributed across the globe, but they seem to be lining up. So if we take a look at where they're lining up, there's a bit of overlap with our previous features. So we find earthquakes in belts, and again, this is where do earthquakes occur. So earthquakes occur in belts, along mid-ocean ridges, in oceanic trenches, in mountain belts, some areas are sparse in earthquakes. They occur sometimes or very rarely. So again, it's not evenly distributed across everywhere. Some areas are more prone than others. We find them in the southern Eurasia High, in that Tibetan Plateau I was just talking about, the Himalayas. So they can be found in the interior of continents as well. So now we're going to take a look at volcanoes. Where do most volcanoes occur? Well, each of these little orange triangles is showing us a volcano. And this doesn't mean that they are erupting at this moment, but it means they have been fairly recently active. So, what do you notice? Do you notice any overlap with where we find earthquakes, or where the features that we discussed in the first slide are? So answering that question, where do we find most volcanoes, They occur in belts. That sounds familiar, huh? They occur along mid-ocean ridges. And in this map, we don't have all of them shown, but basically the entire mid-ocean ridge, where you see that dark area along the middle of the ocean, that should have volcanoes all the way down because magma is reaching the surface all along that point. So the mid-ocean ridge, at oceanic island arcs, in mountain belts next to trenches, at the Red Sea and East Africa, so that area on the southwest coast of Saudi Arabia, and again, just like with earthquakes, they're sparse in some regions, so we don't find volcanoes absolutely everywhere. We find them in some specific places. And lastly, we find island arcs next to trenches. Okay, we will find volcanoes in island arcs next to trenches. So, do you see any similarities? Is there a relationship between where earthquakes occur and volcanoes? Okay. Take a look back at your notes, see what you think. We'll bring it all together in a moment. Right now I want to look just at elevation. So the brown areas are the highest areas. The green areas are lower areas, and you can see the same thing in the oceans with the light blue being lower and the darker colors being higher elevation. So what we notice here when we're taking a look at these elevations is most continents are gentle and low. Mountains occur in belts, meaning they line up. They cluster together. Some mountain belts are found next to trenches, next to oceanic trenches. Mountain belts and high regions are found across southern Eurasia. Okay, so what happened there that we have mountain belts and such very high elevations across southern Eurasia? Just something to think about. We have some elevated areas in East Africa and the Red Sea. And there's a large difference between elevation of oceans and elevation of continents. While both of them have relief, meaning there are low areas and there are high areas, they are very different because the continents are so much thicker than the oceanic crust is. Now, putting all of those pieces together and comparing the distribution of earthquakes, the yellow dots, volcanoes, the orange triangles, and elevations, again, the brown being the higher elevations. So when we put these all together, you can see they overlap quite a bit. You're finding earthquakes where you find volcanoes. Where you find volcanoes, you find high elevations, and so on. So, what does it mean? Earthquakes, volcanism, and mountain building are called tectonic activity. Belts of tectonic activity divide the lithosphere into tectonic plates. So remember, the lithosphere includes the oceanic crust, the continental crust, and the upper mantle, right? And it's all riding on that warmer, weaker asthenosphere just below it. So we get belts of tectonic activity where the lithosphere is divided into tectonic plates. Okay, so taking it back to your notes and the questions that you have there, is there a relationship between where earthquakes occur and volcanoes? Certainly, right? We can see they overlap. Do they always occur together? Taking a look at this map. No. Okay, we can see the west coast of South America, for example. So right along the coast of South America there on the west, we can see we've got orange triangles and yellow dots all over the place. But if you look at the plate that's outlined, the Nazca plate has very few volcanoes, if any, on its western border, yet it's outlined completely with earthquakes. Okay, so they do not have to occur together. The next question being, is there a relationship between the hazards mentioned, meaning volcanoes and earthquakes, and major mountain belts? Okay, so let's take a look at some of our major mountain belts. If we look at the North American west coast, we've got the Rockies and all sorts of volcanoes and earthquakes. If we take a look at the Southern Eurasian High in the Himalayas, where India meets the rest of Asia, absolutely all sorts of earthquakes and a few volcanoes. If we look at the Andes Mountains along the west coast of South America, we have very high elevations there, and we get both volcanoes and earthquakes. So, yes, there is a relationship. So after taking a look at the earthquake and the volcanic activity and how they overlap and outline these areas, what does this tell us about the Earth's lithosphere, about that outer rocky layer? Well, this animation here is showing us the outer layer of the Earth, the lithosphere, is broken up into plates that are constantly on the move. So this is showing us how the plates have moved in the past. This is an actual reconstruction of how the continents have moved over time, how these land masses that are now the configuration that we think of for continents have morphed throughout time. It's pretty cool to watch. And knowing that this is how they've moved in the past, and knowing how they are currently moving, directions and speeds, we can project how the Earth is going to look in years to come, millions of years in the future. Pretty cool. So what is going on? We've got these plates. The outer layer of the Earth is broken up into these plates. We know that they're moving around, so how do we describe how they move? We have three main types of relative plate motion. The first is divergent, so the plates are moving apart. The best example of this is the mid-ocean ridge. So we have continental or oceanic plates moving away from one another. The next one is a convergent boundary. So our plates are moving together. And in this case, the case of this image, we've got one plate that gives way and goes below. This is called subduction. And we have an overriding plate. And in this case, we've got an oceanic plate subducting below a continental plate. I know that because if you look at the very top layer, it's this thin, dark layer on the oceanic crust, and on the continental crust it's a thick, light gray layer. So to figure out if it's continental or oceanic, we want to look at the color. Darker color is going to be oceanic, lighter color is going to be continental, and we want to look at the thickness. Very thin crust is going to be oceanic, and thicker crust is going to be continental. And if we have plates that are moving horizontally past one another. They're moving side by side. Then we get a transform boundary. Okay, so side-by-side movement is transform boundary. So they either move apart, together, or side by side. The plates are either diverging, converging, or at a transform boundary. And that word boundary just means you're at the meeting place. You're right where two plates are coming together. Knowing those three basic motions, either convergent, moving together, divergent, moving apart, or transform, moving side by side, we can take a look at our map showing the plates, outlining the plates, in a different way. So if you notice, our outlines are made of different colors now. So the yellow line represents divergent boundaries, the red line represents convergent boundaries, and the light blue or greenish one represents transform boundaries. So let's take the west coast of South America as an example again. It always makes such a great example because it's a perfect active tectonic area to look at. So the west coast is a big red line tracing all along the side, and if we think about the earthquakes and the volcanoes and the features that we saw on the west coast of South America, remember there is a deep trench just on the border there. There are high mountains and volcanoes in the Andes on land. So all of that is occurring at a convergent boundary where the oceanic plate is colliding with the continental plate. Another example we can take is the mid-ocean ridge. So you can see in between South America and Africa that nice almost outline of the eastern coast of Africa and the western coast of South America, where the Atlantic Ocean formed and pushed them apart and continues to push them further apart because the main movement at that boundary is divergent. It's at that yellow boundary. So you'll notice it is interlaced with the transform boundaries, though. We've got both moving apart and moving side by side. So the best example I like to use for this so that you can really grasp it is put your hands together with your fingers interlaced. So both of your palms are facing you and your fingers are interlaced. Then move both of your hands apart from one another. So overall the movement is your hands are moving apart, but in between each finger, your fingers are moving side by side. That is how transform boundaries and divergent boundaries are so very reliant on one another. They connect one another. So the question in your notes, are convergent boundaries located in the same area as divergent and transform? No. If we're looking at convergent boundaries, we find big, long lines of red, right, all along the Aleutian Islands up by Alaska, all along the western coast of Mexico and Central America, again, all along the western coast of South America. When we have a convergent boundary, it's consistent. It's just a convergent boundary. Whereas when we have a divergent boundary, where the plates are moving apart, usually those pieces that are moving apart excuse me, are connected by transform boundaries as well. So you find transform boundaries with divergent boundaries, and you find convergent boundaries typically all by themselves. Okay. I put together these tables here. You only have one table in your notes to sort of combine all of these different terms and concepts together so you have one reference point to see the differences and the similarities for our three different types of plate boundaries. So on the left, you can see it's broken down by convergent, divergent, and transform boundaries. So moving across just the top row for convergent. So the first one is the type of motion. It moves together. So I've got two arrows pointing toward one another. This is typically how I, when I'm taking notes, this is typically how I note a convergent boundary. Two arrows moving together. We call that type of stress compression. And the crustal thickness increases. So a good idea here is to imagine a ball of dough. That dough is going to represent our crust in this case. So if we are compressing that crust, if we're squeezing it in from the sides, what's happening to it? It's expanding, it's squeezing up higher and lower, right? So it's getting thicker in the center. And so the crustal change is it thickens. We have more crust in the center. For a divergent boundary, we've got the arrows moving apart. That type of stress is called tension. And again, with that dough, if we're pulling that dough apart, it's going to be thinning out in the center, right? The thickness decreases. So our crustal change thins. The transform boundary, our arrows are moving side by side. Usually it's easiest to put this at an angle and have one arrow moving past the other. The type of stress is called shear, and there is no change in the crustal thickness. Nothing is moving up, nothing is moving down. If we had that dough, we would just be sort of smushing it from side to side, pulling one side toward you and the other side away from you. It's not getting thicker or thinner. So there's only horizontal displacement. There's no vertical displacement. So if you want a good set of really quick animations to show you how convergence, divergence, and transform boundaries work as far as thickening, thinning, and horizontal displacement, click on this link here and scroll down. You just hit the play button and it'll show you the little animation. It's very helpful. Alright, so for the rest of the table, now we're looking at features that are associated with convergent, divergent, and transform boundaries. So, for a convergent boundary, we do find volcanoes. So again, if you think about the western coast of South America, where we have the trench, and we found volcanoes, high mountains, that was all along a convergent boundary. And so when we have these two huge plates plowing into one another, that causes a lot of friction, a lot of buildup of energy. So yes, we do get earthquakes with convergent boundaries. Our next feature is mountain belts. And yes, we do get mountain belts with convergent boundaries, particularly if we have two continental plates colliding. Then you can kind of think of it like a train wreck. There's none of that subduction. No plate goes below, really. It's just a huge pileup, and you get very high mountains. This is what happened in the Himalayas on the Tibetan Plateau that we looked at. Our next feature, the mid-ocean ridge. No, we do not find mid-ocean ridges at convergent boundaries. And then finally, oceanic trenches. Yes, we do find trenches associated with convergent boundaries. And again, the best example of this is the west coast of South America. There's that very deep trench just off the coast where the very high mountains and volcanoes are. So yes, we find oceanic trenches. Divergent boundaries. We do find volcanoes there. As the plates are moving apart, we have magma working its way up to the surface and cooling right in the center. So we have brand new rocks forming in between where the rocks have moved apart. So anytime we have lava erupting on the surface, even if it's not explosive or very dangerous, it's still a volcano. So yes, we do get volcanoes with divergent boundaries. Earthquakes. Yes, we've got huge plates moving apart, and we have magma working its way up to the surface. So we will find earthquakes. They're not going to be as strong as the other plate boundaries, but we still get earthquakes. We do not find mountain belts with divergent boundaries, but we do find mid-ocean ridges. So the mid-ocean ridge is where the oceanic plate is rifting apart, and so the ridge, you get higher areas on the sides, and we'll go into this in detail in the next slides, but you have a low area in the center where you have the lava erupting to the surface, higher areas on the sides, and the plates just keep moving further apart, and more material comes up to fill in and cools off, and it continues moving apart. So oceanic trenches, no, we don't have any way to get to that very deep depth that you do at a convergent boundary. So no, no oceanic trenches associated with divergence. Transform boundaries. Basically, the only feature you find with a transform boundary is earthquakes. They're going to be near the surface, and they can be very violent. So no volcanoes, no mountain belts, no mountain ridges, no mid-ocean ridges, no oceanic trenches. With transform boundaries, the main feature you're going to find is earthquake. And the best example of this is the San Andreas Fault in California, which is why California is known for its earthquakes. It's this big side-by-side moving plate boundary. And if you want a really brief, great video to show this type of movement, plates moving apart and then diving back into the earth, this is a really neat little video, so please click on this link to see that. Building on the information from that table, depending on the type of crust that's at these boundaries, you can end up with different types of features. So for the divergent boundaries, where the plates are moving apart, if we have an oceanic plate moving away from another oceanic plate, or you can think of it basically as the oceanic plate is splitting and opening up. This gives us a mid-ocean ridge. That's the feature that's formed at an ocean-ocean divergent boundary. At a continent-continent divergent boundary, where a continent is breaking apart, we end up with a continental rift. So that's a totally different feature depending on the type of crust. The same thing goes for convergence. If we have two plates moving together that are both oceanic crust, they have the same composition, very similar density, so one of them is going to give way, one of them is going to subduct or move below the other one. We have a subduction zone, and that forms an island arc, a volcanic island arc. So that's the feature that forms at ocean-ocean convergence. At an ocean-continent convergent boundary, the oceanic plate is more dense, so it's going to subduct below the continental crust. And in that case, we end up getting a volcanic mountain range or a volcanic mountain belt at that subduction zone. In contrast, if we have a continental collision or a continent-continent convergent boundary where two continents are plowing into one another, we just end up with a huge mountain range and a lot of deformation, a lot of faulting. It's going to end up like the Himalayas are today. So there's not a subduction zone. They're not really volcanoes. It's a very different feature that's found just because it's a different type of crust. At the transform boundary, it doesn't really matter. It doesn't vary between types of crust. So you don't need to worry about that one. But just a reminder, calling on the lesson from last week, the differences between continental crust and oceanic crust. Again, continental crust is less dense, it's thicker, and the bonds are very strong. So if you look at this picture of granite, it's all light colored. These are felsic composition, so it's made up of a certain type of minerals, mostly silica and feldspar, that are very tightly bonded. So when you melt that down, those strong bonds make a very thick lava or magma that resists flow. It's really difficult for it to move. So you end up getting more explosive eruptions, more dangerous volcanoes, as opposed to the oceanic crust, which again is always thinner, it's more dense, it's dark colored because it's made up of these mafic minerals. And so the oceanic crust is always going to subduct below continental crust. And you can think of the example of Hawaii, which the volcanoes there are all coming from oceanic crustal material. So those less explosive, less dangerous, you can stand next to them and watch the lava flow type of volcanoes are associated with oceanic crust. And again, that has to do with how the minerals are bonded together and how thick the magma is. So remember that if you change the type of crust, you're going to change the type of features that are generated. Next we have the oceanic divergent boundaries that we're going to go into greater detail on. So now you know the types of movement, you know the features associated, and now we're going to go into the greater detail. So how do mid-ocean ridges form? We know that it's at a divergent boundary. We know as the plates move apart, we have lava reaching the surface. So the oceanic plates move apart at mid-ocean ridges. Another term for this is seafloor spreading. It's forming new oceanic crust on the ocean floor. And the example that we're looking at here is the mid-ocean ridge. You can tell by the shape of the mid-Atlantic ridge that it is mimicking the shape of the continents on either side. The ocean formed as spreading moved the continents apart. So the features that are found at the oceanic ridge, right at the center we have a narrow trough or ridge, and I would like for you to note this on the blank image in your notes. So we've got a little block diagram in your notes, and I'd like for you to label the parts of this mid-ocean ridge. So right at the center is the narrow trough or rift, where we have these arrows pointing to this red material. The asthenosphere rises and melts. Magma rises through fractures in the crust that have already cooled, so it's moving up through the weakest spots through the fractures. And magma erupts or solidifies at depth. This is how we form new oceanic crust. So it either cools off at depth, and as it does that, it forms great big crystals because it has more time to cool off. Or if it erupts onto the ocean floor, it cools very rapidly, and the crystals are very small. So all of these rocks, bringing it back to our 3 rock types from last week, these are all going to be igneous rocks because they're associated with volcanism. They're formed from molten rock that has cooled off. Along the sides, we have the ridge high. There you have hot rocks and thin lithospheres. So what that means, because the lithosphere is so thin at this point, these rocks are just forming. Because they're very hot, right near this source of heat in the rift, they expand, they take up more space, and so they sit up higher than the surrounding rocks that have cooled off more and condensed. So I know this is a odd example, but the example that I think of is me during the summertime. I can't wear all of my rings in the summertime because my fingers get really hot and they swell up like little sausages. When that happens, it's just because I'm hot, it's hot outside, I'm expanding. Okay, the rocks do the same thing. When they're hot, they take up more space, they expand. During the wintertime, my fingers condense. So if I flail my arms around, my rings will fly right off, the same rings that wouldn't have fit me in the summertime when I was too hot. So it's the same idea. Once your body cools, it pulls in, it condenses. The rocks do the same thing. As they cool, they condense, and they're not taking up as much space. Rather than sketching this out, I hope that you labeled the processes in your own words, or as close to your own words as you can. Our next question is, can new oceans form where there was once land? If we think about South America and Africa, and we know that they used to fit together, then the answer to this is absolutely. Oceans can form where there was once land. This series of images shows us how that's possible. So the very first image, we're looking at just the continental plate, and it's starting to pull apart. You can see the arrows there moving away from one another, and as that happens, the asthenosphere is rising up. As that happens, the surface bulges. We get initial uplift from the rising mantle. In the next image, as they continue to pull apart, now we have stretching and faulting that form a rift. In between, this is the rift. Now we have this low area, and what I want you to think about is, why do we have water there already? We're still just looking at the continent. What's that water doing? So some people have said in the past, well, maybe it's coming up along with the lava, or maybe it's all the gases from the lava. It really has nothing to do with what is coming up from below, but instead it's because we're thinning the crust. So take a look in our rift at how thin the crust is there, and how thick it is to either side. Where the crust is thin, thanks to isostasy, we have a lower elevation, and where does water want to pool? It always wants to flow down. It always wants to pool in the lowest, flattest area. So that's what we're creating when we are forming a rift, is a low, flat area where water, as rain falls, it's going to pool in the low, flat areas. That's all. And we have melting, forming magma that's working its way to the surface as well. As this process continues, that can lead to seafloor spreading and a new ocean basin. So all it is, we start out with the continent undergoing tension, right? The stress it's going through is tension. It's being pulled apart. The asthenosphere rises. It makes the surface bulge. It pulls apart, and now we have a rift. As that continues to rift apart, we're melting that continental crust, and now we've just got, in the third image down, we've got pure asthenosphere material reaching the surface. That's why at the center it's black. The rocks there are black and thin. They do not look like continental crust anymore. So we've had a switch from continental rifting, where the continent is just breaking apart and we're still dealing with all continental crust, to seafloor spreading and a new ocean basin. We've switched to oceanic crust because the mantle has a very similar composition as the oceanic crust. And now finally, the last image, the ocean widens as spreading continues.